Appreciate it. Again, spoiler, container security, it's all about the supply chain. And it's a cooking theme. Of course, it seems like everybody uses that. So let me talk a little bit about myself. Again, to expand on what John said, I'm currently a security architect, a chief security architect, and I like to think of myself as a professional contrarian. I have had a podcast in the past. Some people actually have found it. It's been about 10 years. I'm a blogger, a B2B writer, and just your regular InfoSec Bene Gesserit witch. I tend to focus on best practices, and I have been a former Unix engineer and network engineer, so I can get pretty nerdy when necessary, and this is how you reach me. And I will have slides online at some point, somewhere, somehow. We want to start out with a short poll. I wanted to find out where everybody's organization was in terms of using containers. 1, 2, and 3. 1, just getting started, mostly using in development as we refactor applications for cloud native. 2, evenly split between containers and full VMs and or bare metal with an OS and an application stack. Or 3, what's a container? And that will be going on, and then I'll let John step in with the results of that poll in a couple of minutes. But I'm going to just move on because we're a little compressed probably for time. So the supply chain, the software supply chain. What? Containers are software? Sorry, they are. So in case you're not very familiar with what a typical software supply chain is, I, of course, have arranged to have that represented for you with commonly used tools. Basically, a software supply chain is a set of processes that build a product. Your typical CI/CD pipeline, as you'd like to think about it, where you have deliver, deploy, and typically people split up they get very upset about the D in CI/CD, right? Is it deliver? Is it deploy? Most people separate those through release management criteria. But again, you'll see your typical tools, your Jira for plan, Confluence. You'll see, your IDEs for code, your source control systems like GitHub, Jenkins for building for CI, possibly CD, Travis CI, which is a big favorite. Just so that's what you need to think of as your software supply chain if some of the people here aren't as familiar with the software development process. Now that we've looked at the software supply chain, let's break it down a little bit into a container supply chain. I like to think of the entire software release process, what everybody thinks of as a software development pipeline, as a pipeline of pipelines. Because you have infrastructure as code, and one of the sub pipelines that you're going to have is your container supply chain, your container pipeline. And so you'll see I've broken it up into a software pipeline section where you make, say, your WAR file as an example, and then you build your container, and with your WAR file, you get an image, you test your image, and then you publish it to an image repository. So let's talk about some standard supply chain threats that you typically see. I've pulled this from the SALSA security framework, which is a supply chain security model. I highly recommend it. I think it started out at Google, but now it has multiple contributors from private industry. So you bypass the code review. That's a really important element. Maybe you do manual code review for certain elements, but there's an area where somebody could take advantage of that, especially with the new BD algorithm vulnerability that people have seen out there. Without someone really digging into the code, you're likely to completely miss it, and you may miss it even with a manual code review. A compromised source control system. Somebody's compromised your GitHub repository. Maybe there's typo squatting attack. Somebody's modified the code after the source control. Ideally, when your source code should be certified or attested, and in a situation where you're not really doing that, you could have code that becomes dirty or drifts after source control. You could have a compromised build platform. There are plenty of vulnerabilities out there regarding Jenkins and Travis CI. You could have a bad dependency. I think everybody today is pretty aware of the threat against open source software dependencies. Just the other day, NPM had an announcement of a problem with some malware embedded in some commonly used NPM modules. You could bypass CI/CD completely. It should be pretty difficult to do that, but it is still possible depending on the maturity of the environment. You could have a compromised package repo where you store your containers, or you could be, if you're pulling down a public image, that could be compromised as well. You could just have a bad package, but that's just a few of the elements of where you could have typical threats against your supply chain. You also, this is a great document from NIST. I recommend it highly, Defending Against Software Supply Chain Attacks. I think everybody's very focused on supply chain attacks, given some of what has happened in the marketplace recently. This covers not just written code. I mean, it also talks about design elements. It talks about hardware devices. Of course, SolarWinds is on here. Talks about end user device malware. For example, if you have a developer who has an infected desktop or laptop, there's, you know, they call out the Kaspersky antivirus problem, where it was banned actually in the US for various reasons. But you get an idea that when you consider the supply chain, you're thinking about every process element in the delivery of software. So again, example of some Trojan source, the bidirectional algorithm in the Unicode specification, which allows reordering of characters through control sequences. And you can use this to create source code that renders different logic than the logical ordering of tokens ingested by compilers and interpreters. This is a frightening attack, right? Because of the heavy dependency that most software projects have on open source software. And it's very difficult to detect. Right now, I think the only compiler or interpreter that's been adjusted, I think it was Rust, I think has this detection now, but it's still, everybody's pretty much scrambling with regards to this vulnerability. So what does supply chain security mean? We've talked about essentially what a software supply chain is, but let's talk about the secure elements of a supply chain. It means adding assurance to the software development process, creating confidence and trust in the source material and the practices used. You're trying to get a holistic, high-level view for protecting each phase in the software development lifecycle, and you're approaching the SDLC as a set of business processes. I think this is really important. I think as technologists, we get very caught up in the technology, and I really think of DevOps as a set of automations of business processes, right? That's really what we're looking at. And when you look at it that way, then you can think about the securing of those processes. And it's validating the final product meets a reasonable set of security criteria to ensure that it's not vulnerable. And this is not a new thing. We've been talking about supply chain security for a very long time. As long ago as I've been sitting in on these talks with regards to network equipment, for example, and how code is delivered to network equipment, and even how network equipment is built. I think it's just become very high profile since SolarWinds. So now we're in for the fun stuff. What is a container? I like to think of it as just a bunch of software ingredients. I think Docker has a really good definition. Everybody knows what Docker is. I think it's fortunate or unfortunate, they've really popularized and really opened up the world of containerization through ease of use, right? They have a high-level container management system that everybody has probably used at one point or another. And now we sort of think of we think of a container in the same way you think of Kleenex to tissue, right? Docker is to container. And Docker refers to it as a standard unit of software that packages up code. It's a container image is a lightweight, standalone, executable package of software, right? It's portable, it's modular, and it sort of encapsulates that idea of working fast and working at velocity and ease in DevOps. So let's talk a little bit about virtual machines versus containerization. I think a lot of people are very, very familiar with virtual machine technologies. And depending on what your role is as an audience member here, what your role is in your organization, you may be less familiar with the differences between virtual machines and containers. Essentially, the most important thing to take away is that virtual machines or guests have their own kernel, their own host operating system. They do not share the operating system of the hypervisor, of the bare metal system, right? They have dedicated memory space. There's nothing shared there. While containers share a host operating system. A container runtime then is responsible for helping to create those dedicated spaces, but you are sharing memory space, you are sharing a kernel. This will become very important later as you think about the attack surface. And just to point out, we have multiple container runtimes that we'll be discussing here. There's Containerd, there's CRI-O, which is a Red Hat OpenShift runtime that's become popularized. Then you have low levels like runC, you have gvisor, you have Kata as well. So user space versus kernel space. As I mentioned, you're sharing kernel space with containers. So virtual machines run their own isolated kernels. There's no shared memory or execution space, as I mentioned before. Without the addition of virtual machine technologies, for example, you'll see something like Kata containers or Firecracker or gvisor. So without the addition of that virtual machine of like they call it a micro VM, containers will share the same kernel. Linux namespaces, capabilities, seccomp, SELinux, AppArmor, cgroups, they can be used to enhance segregation between running container instances on the host, but you've still got that sticking point of sharing the same host kernel. So what does a container look like? Well, I like to think of it as a cake. You kind of start at the top and work your way down. And that's pretty much what happens with a container. It's a layered file system, and each layer corresponds to instructions and scripts or a Docker file. OCI compliant runtimes, they use something called a union file system, which has some of the properties such as it's a logical merge of multiple layers into an overlay file system, read-only lower layers and writable upper layers. You begin reading, again, like you start eating from the top and you work your way down, and it's copy on write. I'm not going to go too much into detail here, but I did want to introduce something called lazy pulling. I haven't done a lot of research yet into the attack surface of lazy pulling, but basically, as opposed to the traditional way that you upload a whole container, when you run it and you start it, with lazy pulling, you do not do that. You pull as needed. So it's breaking it up into multiple little bundles that are grouped together logically. So it encourages faster start time. I'm not going to go into too much detail. I encourage you to research lazy pulling because it is starting to become a reality. It's not baked into the OCI standards yet, but I anticipate it will be. Let's talk about high level versus low level runtimes and management systems. I think this is important to understand because when you hear about new vulnerabilities, for example, with container D or run C, you need to understand where the demarcation point begins and ends, right? For example, with some high level container management examples, you have these are referred to by Kubernetes as container. Well, it can be referred to as the container runtime interface. You have Docker, which is a very high level container management system. You have Podman, which is on Linux, and you can interact with containers. You can build using Podman or start them. You have high level container runtimes, again, CRI-O, container D, Docker. I know it's confusing, but there's the Docker management system, and then there was a Docker runtime, which was container D, but has since been donated to the CNCF, I believe, or maybe the Linux Foundation, pretty much the same thing. And these are all part of the OCI. And then you have the low level container runtimes such as run C, which we all know in Kata and gvisor. Kata and gvisor, as you'll see, have sandboxing or virtual machine technologies integrated into that. I think this is important, as I said, when you're looking at container vulnerabilities, because sometimes you'll have a run C vulnerability or you'll have a container D vulnerability, and container D is really a wrapper around run C. You need to understand where the differentiation is when you're looking at that attack surface. I recognize this is sounds like a lot of nonsense, and it's a lot of detail. And I put in a lot of links in my references, which will be in my slide deck, which will be uploaded. And also, as I'm going through this, it can be very overwhelming. I recognize that. So let's try and break this down a little bit. So where do you get your container? Let's talk about, and yes, you'll notice I had a dirty kitchen. Let's talk about your recipes for container images. So you can pull a base image down from Docker Hub, from another public or registry, or maybe a private one. Maybe your vendor that you have a vendor that you work with. They've containerized their software and they have a private registry that's only available to customers. And then you could either add code and configuration, or you can just run it as is. You can use a multi-stage build, which is something I recommend, selectively copying what you need in the image. Without using a base or parent image, you can build an entire OCI compliant image yourself with a tool like Builda. That's for the super paranoid or the super nerdy who are not as lazy as, say, I am. Don't want to build everything from scratch. You can create a single layer from scratch. This is actually a thing. It's a no-op. You're basically just telling the system to get a statically compiled binary. Oddly enough, that will actually send your most security container security tools into a tizzy. They don't understand from scratch no-op images. You can also make a distroless image that only includes the application and runtime dependencies. So I recommend using the best ingredients, of course. You want to use a trusted source for base images, especially as I'm sure people follow reports and the news about how you'll hear about some Docker Hub image that's been compromised and has Bitcoin mining elements in it, and nobody knew. They just trusted Docker Hub and they downloaded it and used it. You want to validate the image with a container security tool. Even I would recommend, let's say you get an image from one of your vendors and you're going to assume that it's okay because you got it from your vendor, validate it. I have found tons of problems with vendor images, even vendor security container images. I recommend using a software composition analysis tool and or a container security tool. There are plenty out there. You want to economize. You don't want to add elements that aren't necessary for your microservice, right? You don't want to have unnecessary ports open. You don't want to have shells. You don't want to have, I've seen package managers in containers. There's no reason to have that on your container image. You want to limit syscalls if you can. I know it's challenging to do that, but it really helps reduce your attack surface if you can manage to do that. Parameterize. Don't hard code configs or embed credentials and secrets in your image. The same thing that you would hear from OWASP regarding, recommendations in the ASVS. Okay, they apply here because remember what I said, right? That a container is a software package, essentially. Reduce, follow the principles of least privilege. Don't run root processes. Don't run your container as privileged. You don't want to, as I said, immutable. You don't want to add a shell. You don't want to log into a running instance. I've been at places that had something where we called it a dirty container. That meant that we detected when somebody logged into a container or made a change, and then we immediately would expire that running container image. You don't want to run a shell for that very reason, right? It's just a temptation, right? There are techniques, of course, with Kubernetes where you can run a container exec. I don't recommend that either. There are alternative debug things that you can do, techniques that you can use that will replicate the environment in another namespace or another cluster so that you can actually troubleshoot in a better way. Minimize, you want to use techniques like distro lists and from scratch to eliminate unnecessary elements and layers. You want to automate. I think automation is probably one of the best elements that will help you attain separation of duties. And it will eliminate errors and it will minimize your attack surface if done well. Then you can also integrate security validation at multiple phases of your pipeline as well. So fry, bake, and buy. If you're familiar with infrastructure as code, where you have this idea of baking versus bootstrapping an image, there's something similar in the concept of containers. You have fried images, which are custom built or extended third-party images, deployed but changed during bootstrapping activity. So for example, if you were to instantiate an image and you do an apt-get or a curl, that is not an image that you can attest. Bake, that's a custom built or extended third-party image, fully created with all the dependencies as part of a supply chain. It's attested and immutable. You can also buy, as I mentioned before, third-party or vendor images deployed without changes, attested and immutable. Okay, I think you know where I'm going here. Bake or buy, but never fry. And I think I just want to go back a couple. So container mistakes. I want to emphasize this heavily. I think what I see a lot is people haven't sufficiently refactored their applications for microservices. So they do a full dump of their virtual machine or AMI into a container. This is a really bad idea, not just in terms of bloat, but also as you saw that I mentioned about the best practices, you get a really large attack surface. Every time you add something into that image, everything that's not necessary and is present on your container image, it increases your attack surface, not just the bloat element. You just don't want to put your entire monolithic application stack in a container. I have this pet peeve. People will refer to container as the image or the running instance. They're very different phases of the runtime. So let's be sure that, like, I'm very particular, I will call it a container image and then a runtime container or a running instance. I think that's important to remember when you're talking about containers, because it's a very precise part of the life cycle. So we've talked about the recipes, we've talked about using the best ingredients, we've talked about fry, bake, and buy. I wanted to share with you a sample container security validation at a high level, so you understand what I'm talking about when I talk about the container security supply chain. So I've broken it up into 1A and 1B. 1A is third-party images, and 1B is a full custom-built image. You'll see that of course, you can use Docker, you can use Builda, you can use Podman, you can download the image from Docker, you may upload it to a tool like JFrog Artifactory. I mean, there are all kinds of different ways, like some things that you're familiar with. There are lots of ways that you can create the image and then you can get it uploaded to a container repository. So what do I mean when I say container security validation? What that means is the container has to meet a certain set of security criteria to receive a passing score, right? And that includes certain elements. In my experience, what I've used is an overall CVSS score. And I might, for example, say that the score has to be less, it can't be equal to or greater than 7. That's an example. I may check to see if there are any root-owned processes in the container image. I might also check to see that the container doesn't run as privileged. And I may look through the container image to see that it doesn't have a shell installed. Most tools out there will look for all kinds of other things. You can check on whether or not some of the open source elements violate your license, your agreed licenses. Like you've decided certain licenses aren't okay to use in your organization, maybe because you make software. So you can check for all of that. And then that becomes part of my policy for passing or failing a container image. And then once I've done that in the actual build phase, it's okay to upload to a repository. And then I do an ongoing scan of the images in the repository. And then when the container is deployed to runtime through a pipeline, then a runtime control component ensures that only security validated and even signed images are deployed and can run. Signing can be challenging sometimes depending on what your pipeline tools are, but it's valuable because it gives you an extra level of assurance that your image has not been changed. So let's talk for a minute about container orchestrators. I'm sure everyone has heard of Kubernetes. That is a container orchestrator. It's not a container runtime. It will have container runtimes with it. It also has a container runtime interface to use other alternative runtimes. But I think it's important to differentiate between the orchestrator, the container runtime, and the container itself. So the orchestrator typically handles deployment and runtime lifecycle of running instances. Now, don't get me wrong, you could just run a container with straight up LXC with, you could use containerd, you could use Docker itself. The benefit of a container orchestrator is that it will scale up your instances and scale them down to meet demand. They come with ingress and egress controllers. It will have container networking. You can have either overlay networks, you can have routing. I mean, far more than you would have normally. You have clustering. It has redundancy and availability options for your hit instances, and also your nodes or hosts where the orchestrator and the running containers are. You have load balancing, service discovery, health monitoring. I think you're getting the picture, right? That this is a complicated beast, but if you want containers to be very resilient in most organizations, then you'll usually use a container orchestrator. You also have the benefit of a multi-tenant segregation option through, you can use network segmentation, you can use resource restrictions, you can use tools like namespaces. Some examples that you're probably familiar with include Kubernetes, OpenShift, and prior to that, Mesos and Nomad, for example. Cloud providers also have managed orchestration options such as EKS from Amazon, you have GKE, you have AKS. And the real benefit, one of the benefits to these orchestrators is the ability to use policies. You can really get a lot of bang for your buck at runtime on Kubernetes, for example, with admission control. It can decide, it can go talk to a container security tool or a policy agent like Open Policy Agent, and it can make decisions about whether or not these containers should run. I am a big fan of admission controllers, for example, on Kubernetes. They provide, that admission controller is exactly what it says, right? Admission control. It's a last gate for a container prior to runtime. And I recommend strongly that if you're unfamiliar with admission control, Kubernetes did have something called pod security policies, which has since been deprecated, but now they have something called, you have security contexts, which were always there, but you also have security policies now that interact with admission control. This is a complicated topic. You will spend lots of time there. So I've been talking a lot, and here's another moment for a poll that we can either talk about now or we can talk about at the end. What container orchestrator are you using? There's self-managed Kubernetes for the win, sure. If you're willing to take on that level of complexity, go for it. There are cloud provider managed Kubernetes instances. If you're worried about cloud lock-in or you're multi-cloud, that may not be the best option for you, but there are tools that can help with that. There's OpenShift, which is especially useful if you're on bare metal. There's Nomad or Mesos if you're still using that. And there's something called Docker Swarm, which did not win really the orchestration wars. You can still use it. I researched this the other day. I don't think that's the recommendation anymore. So maybe we'll look at the poll results at the end, and I'll keep going because we had a late start. So the CNCF, I think if you're not familiar with that, I highly recommend you participate. The Cloud Native Computing Foundation. They're sort of the evangelists of the 12-factor app and cloud native, right? And they have some principles of supply chain security. So this is basically just taken from them. I'm just going to, go over the concepts very quickly. It's this concept of creating trust, establishing trust at every step in the process through a combination of signing metadata and cryptographic validation. The focus that everything that can be automated should be automated and documented. As I mentioned before, DevOps is automation of business rules, hence the documentation. And automation helps get you to separation of duties. It eliminates errors, and it ensures that your attack surface is reduced because now you have something doing things that don't involve people touching it. Every step in the software build and supply chain process needs to be defined with limited scopes. Every actor, whether it's human or machine, needs to have clearly defined roles. It's all about that separation of duties, which then is enforced by automation. And every entity in the system has to engage in mutual authentication. And that it's that trust but verify, right? So that nothing or a human or a machine shouldn't be trusted unless you can verify it. The CNCF has something called the cloud native security landscape. I noticed some questions about tooling. I don't really recommend tooling. That's not why I'm here. What I can do is point you to the cloud native security landscape. There are open source and also commercial tools here. They all have gone through the CNCF and contribute. They're reputable, so I encourage you to investigate it. It's interactive, so you can interact with the online tool from the CNCF so that you can find what you need. I know everybody's talking a lot about components right now, right? Everybody's nervous because of the supply chain attacks and some of the elements that I've talked about. OWASP has a software component verification standard. It's a community effort like all other OWASP efforts, and it helps you in identifying and reducing risk in a software supply chain. I highly recommend that you take advantage of this, and it gives you a lot of ideas of best practices. It points out good patterns versus anti-patterns. And some of the elements, some of the control objectives include having centralized repositories. You really do. That's like probably one of the easiest ways because it gives you visibility over where everything is, right? You want your repositories to use strong authentication and TLS. You want to have auditability, and really it really emphasizes code signing and verification. And I just want to point out, again, this idea of signing and verification and assurance and attestation, that seems to be the theme when you're talking about supply chains. This is from the NIST SP 800-190 Application Container Security Guide. I'm not going to read through this too much. It's a high-level sort of life cycle of how containers are created and deployed. You'll see it's very high level, right? It just says developer over on the left. It doesn't really break it down into what happens so much. But it gives you an idea. I recommend you steal it when talking to executives, for example. It's helpful in that sense. Bombs, S-bombs, and D-bombs. I was at KubeCon and that recently, and that was a big topic, again, because of the supply chain and because of certain executive orders from the White House, given the SolarWinds issue that occurred. There are techniques. I'm sure if your organization is pretty mature, they were already creating S-bombs. If you were a commercial software company, you were probably already using S-bombs, or you should be. But there are tools now that you can create S-bombs for the container itself, which is likely recommended as because what I said was, right, it's a software package. And sometimes people put too much stuff in there. And now it's a requirement in certain sectors to have an S-bomb. If you're in the federal sector, and you do business with the federal sector, you are required to provide an SBOM with each product, or you have to have it available on a website. And I mentioned 2 open source tools, Sift or Turn, that can assist with that. I'm not going to go into too much detail on this because of time, but I have a set of DevSecOps decisioning principles that I use. I think the problem that you get into with DevSecOps is that people think that they confuse information with a decision, and the information isn't all that useful unless you're making a decision, i.e. sort of breaking a build or diverting a build, right? And I think that when deploying things as part of a pipeline, that you need to have decisioning criteria that is very clear. It's based on defect principles or SLAs, so that people understand when is slow path happening, when is fast path, when will my build get broken, when will it get passed. I think what people mistake, DevSecOps, they think, because it's on that, the Gartner overhyped scale, right? Of, so the thing that everybody talks about, but then isn't very effective. I think the problem is that people just think that they push a lot of information out without doing things, and so it's less effective. And if you want to be effective, because the opportunity with DevSecOps is to optimize coverage, then you have to create decision points. And the reason why I'm talking about this is because a real world use case, and you'll notice that I have decision points, right? And that's what I mean by decisioning principles, right? So for example, this is from a place that I recently worked at. I'm not going to say where, but you have the developer who pushes the code, triggers the build, and you're creating the container, right? You'll see the CI system after item 2. It uses an image security validation service to scan the image, and it uses a policy validation service. Maybe the policy validation checks for things that aren't checked by the security system. Maybe you use an open source software SCA tool that only checks packages, and then you have policy validation that checks certain container specific rules, maybe such as trying to run as privileged. That's why we have it separated. That's why we did separate it. Then you have the publishing phase, where you publish to an internal container image registry. Then as part of you need to think in terms of non-prod versus prod, your development and test environment, maybe your QA environment. And the goal is distribution, right? So you start with non-prod, you push it to a read-only registry node. You go through your testing, your functional testing. After it passes your release criteria, I'm hoping that everyone understands release management, where you have criteria that checks. Did it go through unit testing? Did it go through functional testing? Did it pass everything? Hopefully you're not doing too many tests. You don't have too many test escapes. And then if it passes the release decision, then it's distributed or promoted to production. But you'll notice that I have read-only registry nodes that your production and non-prod Kubernetes clusters are interacting with, that nothing is touching the actual core container image registry. And that's a way to ensure that you're not, that this is an assured image, that it's a read-only image, and that it's not something that has had any drift occur. So That was a lot. I know. Okay. Now we're getting close. We're getting close to the end here. I know that was it might have been overwhelming to people. So I just want to go over, I have some reminders here. Small images. It's beautiful. Make your images compact. You leave out unnecessary libraries or binaries that you don't need for your microservice. Trusted registries. Who do you trust? That's really important. And in case you didn't know, you can actually establish trusted registries in your Kubernetes configuration. So you can actually decline to use, if somebody tries to use a registry that isn't trusted, then it won't use an image from that registry. You should validate your images. They should be free of vulnerable libraries and components. And I believe that you should validate anytime there's a state change, anytime somebody touches it, anytime something is it's forked, as I like to say. Container images shouldn't need to run as privileged or have processes that run as root. You don't want to put credentials, keys, or tokens into your image. You want to do just in time with credentials. Reduce the listening ports needed in your container image. You're just increasing the attack surface. You want to use a standard runtime. I know maybe this seems obvious to some people, but not all container security tools, the runtime ones, they basically, a lot of them hook into a runtime. And if you're using some weird runtime that's maybe new, then the container security tool might not work, right? A container isn't a host. It's an ephemeral drop of rain. Shouldn't be logging into it, trying to change it. It's supposed to evaporate. Something interesting you can do that you should try is you should regularly expire your containers. They should they should be changed out every 2 weeks, every 4 weeks if you can. This is about drift prevention. Only attested immutable container images should run in your environment. You want to automate your container builds and deploys, and you want to constantly reevaluate your supply chain. You want to threat model that supply chain, because that is a process that needs to be reviewed as much as your own software architecture or software itself. So that was a lot. I appreciate everybody's time. And now I'm going to,